Electronegativity. Electronegativity, we said, is how hard one atom pulls on the electrons that it shares with another atom. Okay? So let's take a look at a couple of atoms here, and let's see. Well, in fact, we can go back to this. We can start with our electron dot formulas. Okay? Here's oxygen. Here's hydrogen. Okay? So they're sharing electrons so they can be more stable. That gives oxygen 8 electrons, where it's in a form that's more stable. Hydrogen has 2. That's the form that makes it more stable. And we can get our Lewis dot formula. Then this becomes a sharing arrangement. It started with the electron dot formulas, and now we're doing the sharing arrangement, then the Lewis dot formula, and finally the Lewis formula, where we replace shared pairs of electrons with lines. Okay? All right. But these lines mean I'm actually sharing a pair of electrons. Okay? The thing is, they're not shared equally. Okay? If you look at the electronegativity table, and what we did in Unit 2 was, I wanted you to know the pattern. And the pattern is, the element with the highest electronegativity is fluorine. The element with the lowest electronegativity is, for the most part, francium. And there's a pretty clear pattern. It's kind of a bumpy sort of thing in between. But you can pretty much estimate that if the element is more in this direction, it has a higher electronegativity. If it's more in this direction, it has a lower electronegativity. That make sense? Okay. So that's the pattern I wanted you to know and memorize from Unit 2. You can always look up electronegativity when you need to do the math, but in general, you need to know that this is more electronegative up here and less electronegative down here. And we pretty much ignore any electronegativity in the noble gases, even though we are showing a little bit in xenon. Yeah. You can see that oxygen has a much higher electronegativity than hydrogen does. Oxygen has a much higher electronegativity than hydrogen does. Okay? In general, now this is a general thing, there are a lot of factors that in the shape of a molecule that affect electronegativity in the real world. We are going to simplify it down to its simplest definition we can come up with, and sometimes that makes the reality a little different from our simplified system. Okay? But we got a general definition here that will make it a little bit easier for you to do it at this level. Okay? When you get into organic chemistry in college, you're going to have to do it at a higher level. Okay? But for right now, we're doing very, very simple. We're trying to come up with a really simple way of understanding electronegativity so that everybody can kind of grasp the idea, at least in the beginning. Okay? But I'm simplifying it so much that sometimes it's a little bit different from the reality. Okay? All right. But having said all that, let's imagine what's going on between this oxygen and this hydrogen. Okay? So there's a couple of electrons in here. Okay? In that bond. If oxygen is pulling harder on those electrons, and it is, it has a higher electronegativity. The electronegativity for oxygen is 3.44. Yeah, electronegativity subscript O for oxygen. The electronegativity for hydrogen is 2.1. So you can see there's a lot more electronegativity on this end of the bond than that end of the bond. Yes? 3.44. Okay? Well, you can always look on your periodic table about, electronegativities and see for yourself.
Wait.
Yes?
So if oxygen needs 2 electrons in order to be full, how come it has a higher electronegativity than sulfur, but they both need 2 electrons?
How far do you want me to go with this explanation?
Beyond the scope of the class.
Beyond the scope of the class.
Well, not so much. Remember, let's see if I can do it in a fairly simple way, okay? Again, I'm just hitting the highlights here, okay? There are other factors that go into this. But remember the shielding effect? The further out the electrons are, the less strongly the nucleus pulls on those electrons, okay? So if oxygen needs 2 electrons, let me find a periodic table here. Well, here we're going to use this one. Oxygen needs 2 electrons, okay? And its valence level of electrons are a lot closer to the nucleus. Therefore, any electrons it shares in that valence level are being pulled more tightly by the nucleus as well. That's why that's probably the simplest way of explaining why it has a much higher electronegativity. Okay? Because it's how hard it pulls on those it's sharing. All right? All right. So what's happening here is there's really an electron cloud. Now we often draw that sigma bond as being sort of cigar-shaped or wiener-shaped. Okay, remember that from the last unit? Okay. And those electrons are flying around in here at nearly the speed of light. Okay? So they're not really in one place on in this bond. Okay? In fact, there's kind of a whole field where the electrons can be there. What happens is that most of the time the electrons are here. But because oxygen is much more electronegative, they actually end up spending much more time closer to oxygen than they do to hydrogen. So the density of electrons in this bond is closer to oxygen. Now, as you go further and further away from that area, you get to less and less density of electrons. But what this means is the oxygen is actually more negative than the hydrogen is because the electrons are there more of the time. The result is that in the molecule of oxygen, the electrons are around the oxygen far more often. This makes the molecule of oxygen, each individual bond is polar because the electrons are spending more time over here. And this side of this bond is more negative than this side of the bond. This hydrogen over here, poor little hydrogen, only had one electron and one proton. You're pulling on that electron over here like that, it's practically naked. You know? It's just really positive over there. Okay? All right. Now, huh? That I just described what polar means. It's more negative on this end of the bond than that end of the bond. Because the electrons are more over here than over there. Yeah, partially positive. So this end of the bond is partially positive. Partially negative, and this end of the bond is partially positive. Okay. That's the symbol we use. You just sort of like make an S that kind of loops back on itself. Okay? Huh? No, it's electromagnetism polar, not magnet polar. Although they're very much related, but there are some differences. Okay? Well, we can do that, sure. But let me finish this explanation first, and then we'll get back to it. Okay? Now that's the first step in understanding when you have a polar molecule. You've got to figure out the bonds themselves. Yes.
What's that symbol?
That just means partially negative and partially positive.
Okay.
Not completely positive and negative. Those are ions.
So it's kind of like an 8, it's not an 8.
Well, you could think about it that way. Or an S with a closed up loop at the bottom. Huh?
3/4 and an 8.
Okay. All right. So the electrons really, to show this, these electrons really don't belong there. To show it using this sort of arrangement then, we want to put the electrons over here closer to oxygen. That's one way to show that bond is polar, is if you want to illustrate it. Another way of showing that it's polar is to draw an arrow over here and kind of put a plus sign on this end of the arrow down here next to hydrogen. So that's another way of illustrating the polarity of the bond. Okay? A lot of ways to do that. I like this way myself. Okay? I prefer this method. Huh? Well, you wouldn't have an arrow if it's neutral. And if it was neutral, the electrons would be dead in between. Truly neutral. Okay? There are very few bonds that are truly neutral. Yes?
So you put a line over by the 8 and then draw an arrow.
Yeah. Draw an arrow toward the oxygen because that's the direction the electrons tend to travel in. It just kind of puts a plus sign there, kind of, sort of, because that's more positive over here on this end. Okay? Yep.
I like it. It's not unusual compound, is it?
Yeah. OH is not. That's actually a hydroxide, but we're just looking at one bond in the water right now.
Oh, okay.
Yep.
So you said it would be possible for it to be completely neutral?
Yeah, if I have two oxygens bonded together, which happens.
I mean, if there was
Two different elements cannot be truly, completely nonpolar. Okay? but the polarity can be so weak that we consider it nonpolar. We'll talk about that in a minute too. Okay? All right. So what we have to do to find out the polarity of the molecule is to find a three-dimensional shape for this molecule. Okay? So let's see. I've got 4 sets of electrons around a central atom. What shape could that possibly form? Probably a tetrahedral. All right. So here's our modified electron pair shape. Okay? And that modified electron pair shape means we're going to end up with a molecular shape that's bent. Okay? Now, if the electrons tend to spend more time with oxygen, such that we have a direction of polarity that goes in like this toward oxygen, because oxygen's bonds are bent, we get a polar molecule overall. Okay? So the polarity is such that this end of the molecule is partially negative, and out here on this side is partially positive. Okay? Does that make sense? Does the theory make sense? No? Okay.
I feel like if we start applying it to our stuff,
Is he one on our own?
I want to show you one that's not a nonpolar molecule in a second, though. For our nonpolar bond and then a nonpolar molecule, and then we'll let you do a couple on your own. Yes.
So the part where the hydrogen is closest together is more positive, right?
Yeah. Yep. That's right. That's only because that's a bent molecule. Okay, it's bent. Okay, so that you push that positive end over on that side. If they were equally spaced, it wouldn't be happening. Okay. Now, first we need to define what we are going to call polar in here. Okay. This is the part where we try to really make it really easy, and we kind of stretch the point a little too far. Okay. But just to make it easier for us, we're going to do it that way. Okay. So in your text, you have this chart here. All right. If we take the electronegativity of the 2 atoms in a bond, and we subtract, and when we subtract, we get an electronegativity difference anywhere between 0 and 0.3. We're going to consider that to be so small an electronegativity difference that the bond can be considered nonpolar. Okay, it is slightly polar, but it doesn't make a lot of difference in the big picture. Okay, the range that we can call clearly polar is a range where the difference in electronegativity between 2 atoms in a bond is between 0.5 and 1.5. Okay, and then if the electronegativity difference calculated is above 1.7 to infinity, well, that's not even polar at all. We're going to call that ionic. Okay, now there are exceptions to all these things. Remember, we're stretching the point here to make this simple. Okay, but it's a good place to start. What? I'm not going to give you one that is completely unclear. Sometimes you have some bonds that are unclear. When you put it together in the big picture, it becomes a little clearer. Okay? All right. So those are your ranges you need to remember. You have to memorize these ranges. 0 to 0.3, nonpolar. 0.5 to 1.5, polar covalent. 1.7 and above, ionic. Does that make sense? Just got to memorize those. I don't have any other way for you to do it. Just got to know. Well, so if we find the electronegativity difference for this bond, the electronegativity for oxygen is 3.44. The electronegativity for hydrogen is 2.1. So the electronegativity difference for an oxygen to hydrogen bond then is 1.34, which we have to round off to 1.3. Clearly in the polar range. The polar range is 0.5 to 1.5, right? Okay? So if estimating in your head confuses you, there are mathematical ways of figuring this out. Questions so far? All right, let me stop capturing here and I'll